Alright guys, today's a special lesson on differentiating an exponential function. So you've probably seen a lot of exponential functions before. One that's quite pertinent at the moment is the exponential growth of a disease or viral infection that's been spreading across the planet. Obviously it's going to go up, it goes up very quickly because the more people that are infected, the more that they can infect, and so it just goes up and up, and it's called an exponential curve. Population growth is another one for bacteria or germs on a surface. There's a lot of other applications for the exponential function. A lot of energy functions use it, but so the basic form of an exponential function is that given any x, if there's some sort of constant multiplied by some other constant to the power of that x. So forget about the a for a second. The basic form of an exponential function is some constant to the power of x, or a power function. And so obviously that's going to get big quick because that power is just going to be increasing and increasing, and then we manipulate the functions with a constant out the front. But there's a special exponential function, and that is f of x is e to the x. I'm going to tell you why that's special very shortly. But first of all, what is e? Well, e is kind of like pi. It's an irrational number, and it has this definition here. So e is the limit, which we've gone through before, as n goes to infinity of this function here. So let's have a look at what that might look like. Let's have a look at what's going to happen as we go to infinity. So like in the previous videos, we can look at the limit by actually approaching it on our calculator. So it might take a wee while if I went slowly, but let's go 1 plus 1 divided by, and let's make n 1 for this one, and then raise that to the 1, 2. So when n is 1, e is 2. So now let's go up by a power of 10. Let's make n 10. 1 plus 1 divided by 10 to the 10. So when n is 10, e is 2.6. Let's go to 100. See if I can get this going in 1 plus 1 divided by 100 to 100. Get this going in one line of working. N is 100, e is 2.7. And let's make it 1,000. 2.7. So you can see that we've been changing quite a bit, but let's go, what was that, 2.72. So now it's starting to slow down, isn't it? So let's add another 0. So we're just getting closer and closer to infinity. Let's add another 0. Getting really close. See, it's not changing much now. 0, 0, and I think we're going to stop changing very shortly. I'll add a few zeros in there. Alright, so e is about that number there, 2.7182, and it's basically just the limit of this thing here. And there's a lot of other cool maths that go with it, but that's basically all you need to know today. And what's special about this function e to the x is that at any point its gradient is the value of the function itself. So what does that mean? It means that if I go to the point 1, 2.7, and I measured its gradient, so I went and measured its gradient, well, its gradient there is 2.7, and that's what makes this graph so cool. So if I went to 2, the point 2 and 7.4, and I measured its gradient, well, m is 7.4. It's the value on the curve is actually the gradient itself. So we can actually say this, that if f of x is e to the x, then f prime of x is also e to the x. So what that means is no, it doesn't need an apostrophe, that's bad English. It is its own derivative, basically. So how would we derive this thing? Well, let's have a look at some examples. So start with a real basic one. So the constant at the front doesn't change the gradient. So if we were to derive this, f prime of x, well, we know it's its own derivative. So 3e to the 4x minus 1, that must be its derivative, right? And you'd be forgiven for saying yes, but you've forgotten one small detail. We have to times by, it has to be done with chain rule, because inside the function, we have 4x minus 1, so we times by the derivative of the inside function. So derivative here is 12e to 4x minus 1. So yes, it's its own derivative, but we still have to apply chain rule. We still have to times by the derivative of that inside function. So let's have a look at this one. F prime of x, well, this one's going to be, it is its own derivative, but we times by derivative of the inside function. We have to times by the 2. Yes, it is its own derivative, but we have to times by the -5. So the actual e part doesn't change, but we still have to apply the chain rule, still have times by derivative of the inside function. So you can always just write this as the original function, and now we need to times by the derivative of the inside function. So 1 over x is x to -1, so that's going to go to -x to -2, isn't it? So if I'm timesing by this thing, that's going to become a positive, and it's going to be over x squared. So this thing's derivative, or f prime of x, is 2e to 2x minus 20e to the -5x plus e to the 1 over x divided by x squared. Because I had to multiply by the derivative of that thing. And the derivative of that thing was -1 over x squared. -1 over x squared. So there's a couple of examples from Newton's method. Let's have a look at if it was written in terms of Leibniz notation. So notice here that y is e to some function u, and u is x squared minus 9 square rooted, which is x squared minus 9 to the half, isn't it? We like to write it in power form when we take that, when we're taking derivatives. So dy dx, the derivative of this function with respect to that variable x, is going to be the derivative of y with respect to u, so derive the outside function, multiplied by the derivative of u derived with respect to x, so times by the derivative of the inside function. So let's have a look at what dy du is. Dy du, well, it's its own derivative, isn't it? So it's just e to the u. And the derivative of u with respect to x, well, we're going to need to chain rule this, aren't we? So we're doing a chain rule within a chain rule, and that usually happens. I remember doing an assignment where I think I had the chain rule within a chain rule about 10 times, and that was a first year university task, and I hated it, but alas. Du over dx times by the power, leave the inside function, reduce the power by 1, so to -half, multiply by the derivative of the inside function. Your half and your 2 cancel, we're left with x over the square root of x squared minus 9. And so now we have du dx, we have dy du, we can put this all back in. So this is dy du is e to the u times by du dx. Great, and I'm just going to simplify this, so that's x times this thing, that's square rooted, all over, all square rooted, just like that. That is our derivative of this thing. So Notice that what I was doing in here is I just write down all my information, and then I probably should have done this, we didn't need it, but then I get each part, I get dy du, and I get du dx, and I get them simplified down, and I just plug both of those into that formula. So outside function derived times by the inside function derived, but still both of them are in terms of x, aren't they? I still write them in terms of x, and then it's just that multiplication, isn't it? So I've already done my actual calculus in these steps. It's just algebra here, and I'll simplify right down, and that is the exponential function.